Okay, sorry for the late start. Here's where we were last time. We were talking about this big theorem right here. And remember what this theorem says is several things, but the big idea is if you're in two dimensions, and if you have a list of two vectors, the list will help you make a matrix. The matrix gives you a transformation. The transformation gives you a parallelogram. The parallelogram, you notice, has edges that are the original vectors. And with all of that set up, right, again, I haven't really made a statement yet. I'm just pointing out that these things all kind of connect to each other. The statement is about what determinant relates to in these pictures, right? And in particular, we pointed out that the determinant of this matrix, absolute value, will always give you the area of this parallelogram. And again, shocking fact, because algebraic thing on the left, geometric thing on the right, where'd the trig go, where'd the square roots go? It's very, very surprising. And then also, we found that, or stated that, whether the determinant is plus or minus tells you about the ordering of the vectors. Now, keeping in mind that whichever vector is first, whichever vector is second, right? The ordering is a statement about is this clockwise or counterclockwise? And as I have it drawn here, it would appear to be clockwise, right? But the point is that ordering, clockwise or counterclockwise, is determined by the sign, plus or minus, of the determinant, right? And you can connect this then to another fact, and that is whether or not this linear transformation has a reflection or a flip, depending on how you want to think about it, sort of hidden inside of it, right? And so whether there is or is not a reflection in there is also encoded in whether that determinant is plus or minus. Okay, so we talked about all that last time. That's just a quick reminder. Notice that this entire theorem takes place in R2, very importantly. Right? This theorem, as stated here, is just for two dimensions. Turns out, though, there is an analogous theorem in three dimensions, and it is totally analogous, exactly as you would expect. So rather than go through the whole thing, go away, let me just point out what I mean by analogous. Actually, that's not very legible, is it? Okay, let me come back here like this. Given a list, that makes a matrix. Given a matrix, that makes a transformation. Given a transformation, you get a parallelepiped, we call it. It's like a three-dimensional version of a parallelogram. And the exact analogous results hold. So in particular, the determinant of that matrix, absolute value, tells you not area, that's a two-dimensional idea, it tells you the volume of the parallelepiped. Exactly as you would expect, it's just a three-dimensional version of area, if you will. Right? And likewise, it also gives you, by its plus or minus, it tells you, and I'll just do the picture here, it tells you whether this list, A, B, C, is right-handed or left-handed, right? And it also, likewise, tells you whether this linear transformation has a reflection hidden inside of it, right? So if the determinant's positive, then there's no reflection hidden inside of that transformation. If it's negative, there's a reflection in there somewhere. Rotation, shearing, magnification, stretching, all these kinds of things, but there's got to be a reflection in there as well if the determinant's negative. Okay, now how to prove these theorems. So now notice we have two theorems. We have the two-dimensional version, and now we have this three-dimensional version. I know two ways to prove these theorems. One is what I'm going to call tedious brute force. And I don't think that's particularly instructive, and I don't think it's a good use of our time. So I don't particularly advise that you look through that. There is a much better way to prove this theorem, these two theorems. Much better, very powerful. Generalizes to n dimensions. It's very cool. And it is actually pretty sophisticated. That proof is, when I taught Math 221 long ago, I showed my students in Math 221, and it was the upper end of appropriate for Math 221. So it's not that you can't do it, it's that it's a little too much, I think, for this class. So I'm just not going to prove these theorems at all. We're not going to be able to prove everything in this class. That's not really what this class is about. Yes?
What do you mean by squished?
So you remember from linear algebra this idea of singularity, right? So some matrices are singular, some matrices are non-singular. And so when I say R3 is squished, another way to say that is that this linear transformation T has a singular matrix. So the determinant 0, the image is of lower dimension than the domain. There is a non-trivial null space. There's a non-trivial kernel, depending on how you want to say it.
So
but yeah,
it would be two-dimensional?
At most, possibly less, possibly one-dimensional, possibly zero-dimensional. Yeah, but definitely not three-dimensional. Right. Okay. Okay, so don't worry about the proof of this theorem. Just doesn't really quite fit in well with this course. Okay, so moving along, we'll talk about cross products now. Here's the definition we're going to use for cross product. It is not, at a glance, clear why we would care about such a thing. Right? It's kind of a weird, arbitrary-looking formula. Turns out it's not. Turns out it's a powerful, wonderful formula that makes loads of geometric sense, and you just can't tell by looking. All right. Now, for whatever it's worth, I've used cross product many times in my life, and I have never memorized that formula, nor looked it up. I've never needed this formula, because a much more convenient formula to memorize instead is this one. Now, there's a catch. This formula is vaguely nonsensical. I'll put this here. Vaguely nonsensical in the sense that, look at this, I appear to have a 3x3 matrix there, but wait a minute, some of the entries in this would-be matrix are not numbers. And can you do that? Is that legal? It brings up some nasty questions. Right? So let's not worry about that. I'm just going to call this a symbolic matrix. When I say take the determinant of this symbolic matrix, I'll call this a symbolic determinant. And all I mean by that is ignore the fact that this is kind of suspicious looking, right? And wait a minute, can you even do that? Is that a thing? Just let that slide. And so we're going to compute this determinant in the usual way, namely, we're going to go across the top row. We're going to, for example, take E1 and multiply by the determinant of this submatrix. And then we're going to subtract E2 times the determinant of that submatrix. And then we're going to add E3 times the determinant of that submatrix. So y'all remember cofactor expansions, right? So just go through that usual formula, and what you're going to find, conveniently, you get exactly that. So, for whatever it's worth, I advise not wasting your time with that formula. I advise learning this formula. It's much easier. Look how nicely organized this is. Standard basis vectors across the top. First vector, second vector. Couldn't forget it if you tried. Right? So, much easier to remember. Okay, pausing. Questions. Anybody have a question? Yeah.
Kind of like a general question, but when would you use I, J, and K instead of E1, E2, and E3?
I personally never use them because I don't see the advantage, right? The nice thing about E1, E2, E3 is if I wanted to define a higher dimensional cross product, such as is in the homework, handy, right? Eventually you run out of letters, right? Otherwise, and I guess you could argue that IJK is fewer pencil strokes, and maybe that carries some weight. I'm willing to put in the extra tenth of a second because I just like sticking with one notation that works in every circumstance. Yeah. Yes.
We don't really do cross products that much in my class, but
yeah.
When you do it, is it equivalent to like if the first row was just ones?
No, very much not. So that's right. If you were to replace this with a 1, and this with a 1, and this with a 1, then notice now all 9 entries are now scalars, and that would give you a determinant that is a scalar, and a cross product cannot be a scalar. Cross products are vectors. Yeah, no, that's a great question. A lot of students get tripped up on that. E1 is not a 1. E1 is a vector. It's a vector, one of whose coordinates is 1.
Oh, okay.
Right? But it itself is a vector. Yeah.
So
Yes.
you're like literally multiplying the vector by the determinant.
Yep.
The determinant
Yep.
of each. Okay.
Totally. Yep.
So are those always the standard basis vectors? Like 1, 2,
Yeah,
3?
this is a very standard notation, no pun intended, that E1, E2, E3 are the standard basis vectors. Yeah, totally.
And that's always what they're equal to.
I'm sorry.
And are they always equal to?
E1 is this, and then E2 has the 1 in the second position, and E3 has the 1 in the third position. Yeah, oh yeah, no worries. So it's just the IJK, right? It's just a better notation for IJK. Yeah. Okay. So, all right. Now, what do we do with this? Here's a little bit of algebra. Recall we have this formula for a cross product. There it is. I'm going to see what happens, no pun intended again, when I dot it with another vector. So now we have our cross product of A and B, and I'm dotting C with that cross product. And when you crank out that dot, and if you just notice what's happening when you do that. So C1 times A2B3 minus A3B2, the first multiplication that you do in this dot product is the first multiplication that you would get when you were taking this determinant. You would have C1 and then times the determinant of this little submatrix, and oh my God, it's the same thing, right? And then likewise, as you proceed down the dot product, you're literally just proceeding along that top row in your usual cofactor formula. So, weird. And by the way, you could take the point of view that this is a pretty good motivation already for why we would care about cross products, right? Where did this formula come up in the first place? And actually, historically, I'm not sure about that. But it would seem pretty reasonable to me that if someone was already interested in determinants, then they would notice that as you take a determinant, you're kind of doing a dot product. And that makes this thing here, part of what you're doing a dot product with, kind of interesting. Okay. All right. So anyway, for whatever it's worth, this is called a triple product. This expression right here. Let me say it this way. Triple product is this expression where you have a dot product with a cross product. It is, as it turns out, always a determinant, which brings up the question, why do we have a new word? Why do we call this a triple product if it's a determinant? We already had the word determinant, right? And the reason why is determinant is something that you do to a matrix. Triple product is something that you do to a trio of vectors. Now, to be fair, yes, those vectors create the matrix, and yet, technically, a matrix is a thing. It's a structure of a certain sort. And a trio of vectors, while it easily makes a matrix, is still not technically a matrix. It's a list of vectors. So, minor little distinction there. Thus the name. Okay. Also, a very minor point, and this is nothing to be too worried about, but you can actually get yourself slightly into trouble if you don't keep the dot and the cross in this order. I think it's a really good idea. You don't technically have to. I think it's a really good idea to always put the cross product on the right of the dot product. There are little micro subtlety issues that you can find yourself on the wrong side of if you for whatever reason feel the need to put the cross product on the other side. Yeah.
So are like C1, C2, and C3 scalars, or are they?
Yeah, that's right. Because C1, C2, and C3, these numbers are just the coordinates of that vector.
So you would just get a scalar out of the.
Yeah, that's right. A triple product is a scalar, just like a determinant is a scalar. Absolutely. Yep. Absolutely. Okay. So, by the way, why do we care about this formula? Why is it a big deal? We know useful geometric information about determinants. We know useful geometric information about dot products. And as we go through, and if you look at the arguments that I'm going to be waving my hands at as we go through this stuff, you'll see that our knowledge of determinant and our knowledge of dot product is going to help us answer questions about cross products. So, and it's going to come out of, a lot of it anyway, comes out of this exact formula. So this is what I like to think of as a good foot in the door for drawing a lot of very powerful conclusions. Okay, so now, bad news. Bad news for me. Maybe good news for y'all, depends on how you look at it. I mentioned this before, but we don't have time to go through these proofs. The proofs are tricky enough that if I can't go through them in class, I don't feel I can, by reasonable rights, hold you responsible for them. So you are not responsible for these proofs. You don't have to look at them. For the remainder of my notes in this section, all these proofs you're not responsible for. Now that said, there's some really cool ideas in here. If you want to understand, if you want to have a good intuition, geometric sense for why these theorems are true, and I distinguish that slightly from why they should be true. These proofs are actually really great for that. Again, you're not responsible. You don't have to. It's not going to be on the test. But if you want to build some geometric intuition, I think it would not be wasted time to try to think about how these proofs work. You can just follow through them, and they're right here in the notes. I think it's a nice exercise. But again, you're not responsible. You don't have to. Still, that's my sales pitch for I hope you will. Okay. So what you are responsible for, of course, are the theorems themselves. So, for example, this one, arguably the first thing to say about cross products, why we care about cross products. Cross products are always orthogonal to the input vectors. A cross B is always orthogonal to both A and B. Neat trick. Let me say that a little bit differently. If you find yourself with two vectors, A and B, and you want to find a third vector that's orthogonal to both of them, cross product. We'll do it. That's the move. Take a cross product. Okay. All right. Here's another fact. Neat fact. If I can get this to behave. There we go. This right here. Now, at a quick glance, this might look like it's some sort of like version of like associativity or something. You remember the associative property of multiplication, right, where you can kind of move parentheses around and whatever, it doesn't really matter. Then at a closer glance, you realize that is absolutely not what this is, right? There's two different operations here, dots and cross. And I like to point out, just as a for example, B in this first expression is part of the cross product. And in the next expression, it is not part of the cross product. So these two expressions that we're looking at here that I'm claiming are equal are pretty substantially different expressions. And so claiming that these are always equal is not just some, trivial sort of immediately algebraically obvious type of thing. It's really not. This is a kind of a deep statement, really. Right? So, neat fact, though, another way to say this is that triple products are preserved by cycling. So remember the idea, if you have a vector on the left, and if you move it over to the right, so what had been in the first position now is showing up in the third position. When you cycle a list, the triple product is preserved. It doesn't change by cycling. So, neat fact. And again, it's a neat fact that's true for neat reasons. And you don't have to, but I hope you will. Take a look at those reasons. Okay. Next fact, and this one really is shocking. And again, you don't have to read the proof, but powerful result here. If you have two vectors and you take their cross product, the magnitude is the area of the parallelogram defined by those two vectors. So specifically, these two vectors, A and B, right, here they are. There's A, there's B. What I mean by this notation here, and by the way, this new notation, probably haven't seen before. Two parallel lines followed by a couple of vectors. As it kind of sort of suggests, this is the parallelogram defined by these two vectors, A and B. So it's this parallelogram down here. Like that. So weirdly, and again, I think really unexpectedly, the cross product and that parallelogram are related. The magnitude of the cross product, the area of the parallelogram, always the same. Super weird. Everybody with me? Everybody happy? Okay. Really cool proof. I hope you'll take a look. You don't have to, but it is pretty neat. I am going to say something really quick about this proof, super quick, and that is just to talk about the sort of the strategy, the structure of the proof. Most of the time, when you want to prove that two things are equal, what we do is we start with one and we plug and chug until it looks like the other, or maybe sometimes we go the other way. We'll start with the other and plug and chug until we get the one, and just try to turn one into the other, etc. Different move here. The proof here is to consider a third thing that I pulled out of nowhere, right, and compute this third thing two different ways. And what you'll find is that if you compute this third thing two different ways, it'll connect to that by way of the first calculation, it'll connect to this by way of the second calculation, and then with just a very slight little bit of algebra, you get that these two green things are equal. So it's what I like to call a mathematical bank shot to reference billiards, where if you want the ball to go in that pocket, you shoot that way, and it bounces off the wall and it goes in, right? So we wanted to know these two things, so we start off by going a totally different direction. And there's several examples in math of mathematical bank shots being a very powerful method of proof. Yeah.
One question.
Mm-hmm.
Is that on the inside of the area right
Mm-hmm.
there?
Yeah.
You put like the sign, like that sign right there, like half of the magnitude or something? I'm not sure what that is supposed to be. Like
yeah. This is just a notation representing this parallelogram.
Oh, okay.
Yeah, it's just a notation for and I totally get where you're coming from. This does look like just the left half of the magnitude notation, but that's just not what that means in this case. Yeah, tragically, there's only so many symbols, right? And math is huge. There's so many different ideas, and so we reuse notations. And sometimes a superscript means you're raising a number to a power. Sometimes it means you're taking that many derivatives. Sometimes it means something else. Yeah. So in this context, that just means parallelogram. Yeah. Okay, let's see. Moving along. Cool fact about what happens when it's 0. I'm going to first say this wrong on purpose in my defense, right? And then I'll fix it. Let me remind you that there's an old fact about dot products being 0. Right? If the dot product is 0, the vectors are perpendicular. Okay, or there's something with the zeros, right? But let's not worry about that for the moment. Dot product equals 0 generically means the vectors are perpendicular. When the cross product is equal to 0, generically that means the vectors are parallel. And then again, annoying. Okay, yeah, there's a possibility that 0 might be involved. And technically, if one of the vectors is 0, they're not technically parallel. But what is always the case is that they're linearly dependent. Right? So, to be precise then, when the dot product is 0, they're orthogonal, which usually means perpendicular. When the cross product is 0, they're dependent, which usually means parallel. And so it's kind of a neat little sort of duality there, that dot product and cross product in this way kind of relate to perpendicularity and parallelness. So they're sort of complementary to each other. Yeah?
Doesn't that also mean that like B is scaled when there's an A, or like they're on top of each other?
Yeah, that's right. So that's right. Two vectors that are parallel one will always be a scalar multiple of the other. Yeah, totally. Yeah, which is just another way of saying linearly dependent when you have two vectors. Yeah, totally. Yep. Okay, again, take a look at the proof if you're so inclined. Here's another theorem that I'm going to state incorrectly, just for convenient intuition purposes first, and then we'll fix it. This list, first vector, second vector, cross product. This is not ABC. This is a very specific list. A, comma, B, comma, specifically the cross product of A and B. That list will always be in right-hand order. Again, okay, well, unless technically there's always the possibility of zeros. God, those are so annoying. But so to be fair, it's never left-hand order, right? And so it's generically right-hand order. It's usually right, except for annoying anomalies, it's right-hand order. But yeah, sometimes there's annoying anomalies, and technically it could be neither. And so, but the key point is never left-hand order. Okay. Again, cool proof. Again, take a look if you're so inclined. But nice, useful rule. By the way, this gives rise to something called the right-hand rule. I don't know if y'all have heard of the right-hand rule relating to cross products. It is just an observation based on the fact that this list is in right-hand order. Right? So, first vector, index finger. Second vector, middle finger. All the usual rules apply. No hand yoga, etc. Right? First vector, second vector. Your thumb of your right hand will point in the direction of the cross product. So this resolves the question of, well, wait a second, there's actually two different directions that are perpendicular to these two vectors. There's that one, and there's that one. Two different directions, both perpendicular to these same two vectors. The right-hand rule tells you which of those two it's going to be. Yeah?
Can you show visually what it would look like if it was left-hand order and why that would be wrong since using your hand?
Yeah, so first vector, second vector, left-hand order would mean that the third vector is in this direction. And what I'm claiming is that the cross product will never do this. It just doesn't. Now, if you want to know why, then I'd have to talk about the proof, but again, that's, that's not really part of the course.
Okay.
Yeah. So this will never happen with cross products.
Okay.
Yeah. Right. Okay, moving along. So our book takes a different point of view. I think I mentioned this in a previous lecture, probably last time, that when you talk about cross products and determinants and clockwise, counterclockwise, right hand, left hand, there's a million facts that all relate to each other in various different ways. And it's kind of like the traveling salesman problem then of how do you get from all of these, what's the best pathway through all of these ideas? And there's zillions of countless different paths through these ideas that you can take. I've written my notes in such a way as to illustrate what I think is the best for our purposes, maximizes geometric intuition, minimizes algebraic pain, inconvenience, algebraic ugliness, right? And the book takes a different point of view. The book's got a focus that's more oriented toward rigor. And that's commendable and good, etc. I just don't think it's quite right for what we're doing here. So that said, I'll, along those lines, point out the book gives a different definition of the cross product. The book gives as a definition of cross product that the cross product is the unique vector that satisfies all three of these properties. And these are the exact same three properties that three of the several properties that we've talked about. So I wrote down a formula, and then I proved these properties. The book assumes these properties as the definition, and then derives the formula from that. Now, take a glance at this section of the book, and you'll see how the book does it. And I think you'll find that it's got a lot of pretty unsatisfying, opaque algebra, brute force, just kind of, it's a lot to wade through. And it's very rigorous, and that's good, but it's not very satisfying, and it's not very intuitively helpful. So anyway, just keep that in mind. Okay. All right. A few more things to talk about. Cross product is not commutative. I think it's always worth noting when things that symbolically, right, we're using the same notation here that we used in elementary school to represent scalar multiplication, which of course is commutative. But we're using this same notation to represent an operation that is not commutative, right? There is, in fact, a minus sign here, so not commutative. That said, even though it's not commutative, it is something, right? After all, there's an equal sign here, right? So something cool happened. And what this is, the cross product, when you switch the order, you don't get the exact same value, but you get the exact negative value. And so we'll call this anti-commutative. Right? And that's a neat thing to know about cross products. But the real headline, the thing you want to make sure that you're very clear on is it is not commutative, and so you cannot just kind of rearrange factors in a cross product in any order you like. It just doesn't work. Okay, the linearity. This will be like our third time through this. I'm going to be pretty quick about this. I made a reference to this on the first day of class. It showed up as a homework exercise. And I'm just going to point out here, just so you can see what it looks like, sort of algebraically looking. This is what linearity of cross product looks like. Specifically, linearity of cross product with a fixed vector A, thought of as a function, is linear on whatever it is that you're multiplying by, in the sense that that function, cross product with A, right, if you put a linear combination on the inside, that's equivalent to doing the same linear combination on the outside. Right, so this, again, it doesn't really quite look like the linearity condition when you just write it down, but the color coding here, I hope, kind of points out how ultimately that's all this is saying, is this is saying linearity. Okay. All right. By the way you're going to prove this, or the way you could have proved this on the homework, is to use facts that we already know about cross product from linear algebra. So you already know from linear algebra that cross product is distributive, and you already know that cross product is scalar associative. And so this expression on the left, if you just kind of apply the distributivity through this plus, and then apply the scalar associativity, sort of factor out the c's, you get this, namely, you show linearity. Okay. All right. Works on either side. In what we're looking at here, we have the function being sort of the left side of the cross product. It also works if the function acts on the right. So, good thing to have thought about. And then super quick last observation, a cross product is also not associative, and no silver lining on this one. It's just not associative. It's just bad when it comes to associativity. These two vectors that I'm claiming here are not equal. There's also no sort of like, it's not anti-associative or anything like that. It's just not. There's just no relationship there. Okay. All right. Okay, a couple of really quick applications. My goal here is not to teach you physics. This is not a physics class. My goal here is to persuade you that cross product is not just a mathematician's dream that just he wrote down on a piece of paper, abstract nonsense that has nothing to do with the physical world. I want to persuade you that's not the case. That cross products are intrinsically, unavoidably part of the physical world. Right? So this is a real thing, in other words. So first let's talk about torque. And I don't know if y'all have previous familiarity with torque, but I'm fairly sure you know what a force is. Right? Force says how hard are you pushing something. Torque says how hard are you twisting something. Right? So it's kind of a rotational analog of force. So in particular, if this is an axis that something's twisting around, and I do a lot of projects with wood at my house, screwing in. I always think of a screw going into a board, right, that I'm tightening either with a screwdriver or very often with a wrench, something like that. So the idea is, and you will notice this if you ever do some wood projects, but the longer the arm of the wrench, the easier it is to turn the screw. Right? So if you have a long-armed wrench and you apply a force, then it makes it a lot easier. Or said differently, if you apply the same force with a longer wrench versus the same force with a shorter wrench, the longer wrench will do more torque. Right? And so, in fact, torque, how hard you're twisting, is computed by this formula, and you'll notice it's a cross product. So, again, it's intrinsic to the world. It's not abstract, made-up nonsense. Is that cool? Okay, another example, and again, this is not a physics class, so let's not get lost in the physics of it all. But y'all know that there exists this thing called a magnetic field, and you know that there exists this thing called a charged particle, electric charge, and movement. These are all ideas that you should be aware of the existence of anyway. So, neat fact, you have a charged particle that is moving. And if it is moving through a magnetic field, and let's suppose that in this general vicinity the magnetic field is kind of coming toward me, as it were. The physical world that we live in, right? Nobody knows why this is. This is just, it was like this when we got here, right? We didn't make this up. But when a charged particle is moving through a magnetic field, there is a force that acts on that particle. In this case, we'll push that charged particle upward as it's moving in that purple direction. And the formula for that force is a cross product. So again, unavoidably, naturally, intrinsically part of the physical world. So this is not abstract, ivory tower mathematician nonsense. This is real physical stuff. Everybody persuaded? Okay, moving along. All righty, let's see here. talk about the equation of a plane. Hope you all have seen some of this before anyway. This typically is covered in linear algebra class. There's some clever ideas of things that you can do with dot products and cross products, and in particular, if you want to write down the equation of a plane, it's a neat way to do it. Here's the foot in the door. If you have a vector perpendicular to your plane and a point in the plane, I claim that there is always exactly one plane that meets those conditions. There's exactly one plane that passes through a given point and that is perpendicular to a given non-zero normal vector. So, given that normal vector n and given that point x naught, how do we write down this plane? How do I write down the equation of the plane? And keep in mind, an equation is a test. So how do I test a point? If I've got some point here, x, let me say that differently. If somebody shows up and says, hey, I've got a point, x, is this point x on the plane? You know, that goes through x naught and it's perpendicular to n. How would I decide if that point is on this plane? And the clever move is to say, well, let's look at this difference vector. That difference vector has its tail at x naught, which is on the plane, and it has its head at x, which, if that's on the plane too, then that difference vector would have to be parallel to the plane. And if that difference vector is parallel to the plane, then these two vectors would have to be orthogonal. Does that make sense to everybody? That turns out to be a nice little test. It's just the geometry just happens to work out very conveniently this way. And keep in mind, orthogonality typically means perpendicular, but it allows for x to actually equal to x naught, which is good because x naught is, in fact, in the plane. So x naught had better pass this test. Right? So orthogonality is actually what we need here. This is not a algebraic version of perpendicularity. This is better than perpendicularity wouldn't cut it here. I need this to be allowed to be zero. Anyway, it's an algebraic test, aka an equation. So, lucky for us. Now, you can rewrite this in a couple of different ways. On the one hand, you can kind of distribute and move things around. That's not much happens there. It's an alternative way to write this equation. For whatever reason, I think this is the more common version. I guess it's got slightly fewer pen strokes. That's nice. But anyway, that's the same thing, basically. And then, of course, very often people like to write things in coordinates. And if you want to write this in coordinates, I claim this turns into that. The idea being that this normal vector is going to have certain coordinates, A, B, and C. And if that normal vector has coordinates A, B, and C, then this dot product just turns into this. And this thing over here on the right, n dot x naught, these vectors are both given. N is given, x naught is given. I know both of these vectors. I can just dot them. I will get some number. We'll call that D. So, again, kind of tempting, and it actually does have some nice features to rewrite this vector equation for the plane into this coordinate equation for the plane. And different circumstances, one or the other of these will be more convenient than the other. I will point out one thing, just as a reminder. Keep in mind there's a temptation to turn a class like this into algorithms and plug and chug and formulas and arithmetic and stuff, and that's not what the class is about, right? So between these two, yes, plug and chug tends to be easier with the coordinate equation, but this equation up here connects more easily to the ideas. This normal vector is important. I can see it in the equation. I can see how a dot product is playing a role here. This dot product is easier to connect to this where in fact this dot product is literally the point. I mean, where this equation came from was a dot product of those two vectors. So this version of the equation is more closely connected to the ideas that actually matter. And this down here is something that might be easier for a computer to understand, but that's, again, not what we're interested in. So resist the allure of the coordinate equation, and try to appreciate the benefits of this vector equation. Yeah.
If the x's are points on the plane.
Do what now?
If the x's are points on the plane, why do we express them as vectors?
Right. So that's right. So this is there's one of the basic facts from linear algebra is that whenever you have a vector space, right, you can talk about points and you can talk about vectors, right? So a point is a location, right? A vector is not. A vector is a direction and a magnitude, right? So they're truly different concepts. But there is a one-to-one correspondence where if you give me a point, I can say, all right, well then I'm going to make a vector by putting the tail at the origin and put the head at the point that you gave me, and that turns a point into what we call the position vector. So for every point, there's a position vector, and for every vector, it's the position vector for some point. So there's this kind of you can think of them as being they're not the same thing, but you can conflate them and get away with it, and context will always make it clear what you're talking about. So now you make a good point, no pun intended, that this x naught here, right, this is a point, but I'm representing it with notation that looks like a vector. And the reason I'm doing that is because I'm about to do some vector algebra, and so thinking of this as a point is I don't need to be thinking of it in that way, right? So this kind of conflation, it comes with a cost, right? But that conflating these two things in this context has some really nice streamlining benefits. And the cost is just that then the listener, the viewer, the reader has to always be heads up as to, wait a minute, what are we doing? What interpretation do I make in which context? And as long as you're always thinking about that, then you'll never lead you wrong. Yeah. Good question. Yes. Yeah.
Where does the D come from?
Yeah, that's just what you get when you dot these two vectors.
Okay.
So these two vectors are both known and given, so you just, it's whatever you get. Yeah. Okay, so quick example. Find the equation of the plane containing these three given points. So there's 3 points. Those points define a plane. I want to find the equation then for that plane. Before I get into the solution, let me point out this is our first example of endless supply of analogous questions where I will give you algebraic information about some geometric objects and then ask you to give me algebraic information about related geometric objects. Right? So here I'm giving you the coordinates of these geometric objects, these 3 points. And what I want is for you to think about the related geometric object, namely the plane, and in particular I want you to give me the algebra, namely the equation for that plane. So when you find yourself with a question like this, you're given certain algebra, you're supposed to find certain other algebra, the first thing I want to say is make sure you realize what geometric things are you given, what geometric things do you need, right? Think in the world of geometry. Don't think about algebra. At some point you might have to do some algebra, but think about what is being geometrically represented by what the question is asking you for and what the question is giving to you. So here we go. We've got these points, and I want to find the plane, which means I need to find a normal vector. So I've got these 3 points. I want to find this normal vector. Notice I've changed it from a question about algebra now to a question about geometry. And now it's just a puzzle. You've got to play connect the dots, as it were. And the tricky, clever move here is to subtract one of the points from the other 2. Realize that those 2 vectors are parallel to the plane, Now, I have two vectors parallel to a plane, and I want to find one vector perpendicular to a plane, and the cross product does exactly that, right? The cross product is exactly a tool for taking two things parallel and giving me one output perpendicular. So thus my normal vector, and then you can plug that into the equation above and get the equation for the plane. And this is a pretty good place to stop it for today. Yeah, we'll draw the line right here. See y'all on Monday. Have a great weekend. See you then.